Tonight, we are going to follow a spacecraft that has traveled so far from Earth that home is no longer a planet, but a moving point, hidden behind the stars. Turning around would not be enough. Earth is moving around the sun. The sun is moving through the Milky Way, and the spacecraft is already carrying enormous speed in another direction. To return, it would need to know where Earth will be years from now, change its velocity, survive the journey, and slow down when it arrives. In deep space, home is not a fixed destination waiting behind you. It is a target moving through darkness, while every mistake grows larger with time. So tonight, the question is simple. Why would returning home from deep space become almost impossible? Before we begin tonight's journey, subscribe if you want more calm space documentaries like this. Leave a like if you enjoy deep space mysteries. And here is a question. If you were stranded in deep space and could send a final message back to Earth, what would you say? Let me know in the comments. I will pin the most thoughtful answer. Tonight, you are watching the Just About Space channel, talking about why returning home from deep space is impossible. At first, returning home sounds almost simple. A spacecraft has traveled too far. Something has gone wrong, and the crew decides to turn back. The ship rotates slowly in the dark until the windows face the direction they came from. Somewhere behind them, Earth is still moving around the sun. Somewhere beyond that, the familiar planets continue along their orbits. The path home seems as though it should be waiting in reverse, like a road that can be followed back to its beginning. When a car turns around on Earth, the road remains beneath it. The ground provides a fixed surface, the destination stays in the same general place, and friction allows the vehicle to redirect its motion. A ship at sea can change course against water. An aircraft can bank through air. In every familiar form of travel, the vehicle moves inside an environment that helps define direction and movement. There is no ground under the spacecraft, no atmosphere pressing against its hull, no ocean resisting its turn, and no visible road connecting one point to another. The ship is not moving across a surface. It is carrying velocity through empty space. Rotating the ship changes the direction it faces, but it does not automatically change the direction it is traveling. To understand why, it helps to separate two things that feel naturally connected on Earth: orientation and motion. Orientation is where the ship is facing. Motion is where the ship is actually going. On a road, those usually feel like the same thing because the wheels follow the direction of the vehicle. In space, they can be completely different. A spacecraft can rotate in any direction while still drifting along its original path. That memory is stored in velocity. Every engine burn, every gravitational assist, every correction made earlier in the journey becomes part of the path the ship is now following. Once the engines stop, the spacecraft does not slow down naturally. There is no air to push against it. There is no friction to gradually remove speed. It continues moving with almost the same velocity until another force changes it. On Earth, stopping is normal. Vehicles lose speed unless power is added. In space, continuing is normal. Speed remains until energy is spent to change it. A spacecraft does not need fuel to keep moving forward, but it needs a great deal of fuel to stop moving forward. Turning the hull is easy compared with turning the trajectory. The ship must not only face Earth, it must change the motion of every kilogram on board. The hull, engines, life support systems, water, food, fuel, instruments, and crew are all moving together. To reverse course, the spacecraft has to remove the velocity carrying it away, then build new velocity in the opposite direction. The farther and faster it has traveled, the more severe this requirement becomes. This is where the idea of just going back begins to break apart. The path behind the ship is not a physical tunnel. It is not a trail suspended in space. The spacecraft has passed through regions that look almost exactly like the regions ahead. There are no tire marks, no fading wake, no line connecting the current position with Earth. The earlier route exists only in calculations, navigation records, and the ship's changing relationship with moving objects. They appear stable because they are so distant, but the spacecraft is moving through a system where everything has motion. Earth orbits the Sun, the Moon orbits Earth. The Sun moves through the Milky Way. Nearby stars move relative to one another. The spacecraft itself has been launched into this moving structure with a path shaped by every force that acted on it. That distinction is easy to miss because human experience treats home as fixed. A house waits at an address. A city remains on a map. A coastline can be found again. Even when Earth rotates and travels around the Sun, the motion is invisible in ordinary life. Home feels still because we move with it. Earth has continued along its orbit since the ship left. The exact point in space where the spacecraft began is now empty. Returning to that location would not mean returning to Earth. It would mean arriving at a place Earth occupied in the past. Home has moved on. If the journey lasts days, Earth shifts along its orbit. If it lasts months, the geometry changes dramatically. If it lasts years, the Sun itself has moved an enormous distance through the galaxy, carrying the planets with it. The spacecraft is not trying to return to a place. It is trying to meet a moving world inside a moving planetary system, inside a moving galaxy. This is why navigation in space is built around prediction. A spacecraft is aimed toward where a planet will be, not where it appears to be at the moment of departure. Mission planners calculate orbits, velocities, gravitational forces, travel times, and possible corrections. Even a journey within the solar system depends on meeting a moving target at the correct moment. A spacecraft traveling to Mars does not point at Mars and fly straight toward its current location. It follows a curved path designed to cross the planet's future position. The spacecraft would need to know where Earth will be when it arrives. That could mean predicting years or decades into the future, while also controlling the ship's own speed with extreme precision. Any mistake in timing becomes a mistake in position. Arriving too early or too late could mean missing Earth by millions of kilometers, even if the ship returns to the correct region of the solar system. A spacecraft approaching the inner solar system at high speed cannot wait in one place for Earth to come around. It would still be moving. The Sun's gravity would bend its path. The planets would pull on it slightly. Every engine burn would alter the timing. If Earth were on the other side of the Sun when the ship arrived, the crew would need enough fuel and control to adjust the trajectory or enter some kind of orbit and wait. To remain near the Sun, it would enter an orbit. To meet Earth later, it would need an orbit that crosses Earth's path at the right time and speed. If the ship arrives too quickly, it might pass through the solar system and continue outward again. If it arrives too slowly or at the wrong angle, it may fall into an unsuitable solar orbit. Even successful return to the neighborhood of home would only begin the final problem of meeting the planet itself. There is another reason the past cannot be followed exactly. The spacecraft's outward path may have depended on planetary gravity assists. A probe can pass near a moving planet and exchange energy with it, gaining speed and changing direction without using as much fuel as an engine burn would require. This is how some missions reach the outer planets or leave the solar system more efficiently. But the planets that provided those assists do not remain in place. A spacecraft that used Jupiter to accelerate outward cannot assume Jupiter will be waiting in the correct position to slow it down on the way home. The geometry that made departure possible may have been temporary. The ship could know the route perfectly and still be unable to repeat it because the planets have moved. The outward journey may have been planned around a rare alignment, a precise launch window, and a carefully timed sequence of encounters. Once those moments pass, they are gone. Returning would require a different route, different timing, and perhaps much more fuel. The universe has not changed its laws, but the arrangement of moving worlds has changed enough to make the earlier solution useless. The spacecraft was designed with certain assumptions: a planned destination, a planned duration, a planned amount of fuel, a planned sequence of engine burns, a planned communication schedule. If the ship suddenly needs to return from deep space, it may be asked to perform a mission it was never built to perform. Every kilogram launched from Earth has a purpose. Fuel is carefully measured. Engines are chosen for specific tasks. Life support supplies are calculated for a certain duration. The ship's structure is designed around expected stresses. Adding the ability to reverse from any point in the journey would require carrying far more fuel, stronger systems, and larger reserves, which would make the ship heavier and harder to launch in the first place. There may be no alarm, no visible boundary, and no sign outside the window. The ship crosses a point where the remaining fuel, speed, distance, and time no longer support a safe return. Everything may still be working. The destination may still lie ahead. Earth may still be visible as a pale point through an instrument. But the practical route home has already disappeared. This is one of the most unsettling aspects of deep space travel. The loss of return may happen long before anyone is in danger. The ship can continue normally, moving through silence, while the margin for going back becomes smaller with every hour. The engines still function. The navigation system still knows Earth's location. Communication may still be possible, yet knowledge and capability are separating. This distinction matters because being lost and being unable to return are not the same thing. A lost traveler does not know the route. A stranded spacecraft may know the route perfectly. It may calculate every burn required, predict Earth's future position, and understand exactly what must happen. The impossibility comes from not having enough energy, fuel, time, or surviving systems to perform the plan. The crew could turn the spacecraft around and watch the instruments point toward the sun. They could receive messages from Earth, delayed but clear. They could see home as data, perhaps even as a faint image. The emotional distance might feel smaller because contact remains. But physical return would still depend on momentum, fuel, and timing. Feeling connected does not change trajectory. This is why deep space is not simply empty. It is filled with consequences. Every earlier decision remains inside the current motion. Every acceleration must later be cancelled if the ship is expected to stop. Every shortcut using gravity changes the geometry of return. Every day of outward travel increases the distance and changes the target's future position. The emptiness does not resist the ship, but it also does nothing to help. Earth's gravity becomes weaker with distance. The sun's gravity extends much farther, but it does not guide the ship gently back to Earth. It shapes orbits and trajectories, pulling according to mass and distance without caring about human destinations. A spacecraft traveling outward may still be gravitationally connected to the sun, yet that does not mean it will naturally return to the planet it left. If the ship follows the wrong path, it may enter a long orbit around the sun, leave the solar system completely, or pass through the inner planets without meeting any of them. The laws of motion remain perfectly predictable, but predictability is not safety. A trajectory can be understood and still be fatal. The farther they travel, the less the word return resembles the journey in reverse. It becomes an entirely new mission, launched from a place with no supply base, no rescue system, and no margin for error. The spacecraft is both the vehicle and the launch site. Whatever it carries is all that exists. That thought gives the title its quiet fear. Returning home from deep space is not impossible because Earth disappears or because every astronaut forgets the direction. It becomes impossible because home is moving, the spacecraft is already committed to another velocity, and reversing that motion requires a new journey more demanding than the first. Every kilometer already traveled remains inside the return calculation. Every second of acceleration remains inside the fuel requirement. Every moving planet remains. Inside the timing, the ship is not separated from Earth by a straight line alone. It is separated by motion that has to be undone. And once Earth becomes a moving target rather than a fixed point behind the spacecraft, the return journey begins to grow far more difficult. That may be the strangest part of returning through space. On Earth, a destination can usually be described by a place. A house stands on a street. A city remains inside a country. A harbor waits on a coastline. Even if the traveler is delayed, the destination does not continue moving millions of kilometers away while the journey is still unfolding. Every second, the planet moves along its orbit around the sun. It does not wait for a spacecraft to catch up. It does not slow down because the return is difficult. By the time a signal reaches a distant ship, Earth has already moved from the position described by that signal. By the time the ship acts on the information, the planet has moved again. The spacecraft must aim not for the Earth it can observe, but for the Earth that will exist at the end of the return. That future position depends on travel time, speed, direction, engine performance, gravitational forces, and every correction made along the way. If any of those estimates changes, the meeting point changes with it. Earth travels around the Sun at roughly 30 kilometers every second. That motion feels invisible from the surface because everything around us moves with the planet. The atmosphere, oceans, buildings, people, and landscapes all share the same journey. But from deep space, the motion becomes impossible to ignore. In 1 minute, Earth moves thousands of kilometers along its orbit. In 1 hour, it moves farther than the distance between many countries. Over days and months, the change becomes enormous. After 1 year, Earth returns to a similar position around the Sun, but the Sun itself has continued moving through the galaxy. The solar system is not tracing a perfect circle through empty stillness. It is traveling with the Sun as the Sun moves among the stars. Earth's path is therefore not a flat ring left behind in space. It is part of a much larger motion carried forward through the Milky Way. That distinction matters because human memory tends to preserve places as though they remain fixed. The crew remembers Earth where it was when they departed. Mission records contain coordinates, departure times, orbital positions, and images of the planet fading behind them. But those records describe a past arrangement. They are not a road back. Even within the solar system, this kind of meeting is difficult. Spacecraft sent to other planets do not fly toward where those planets are at launch. Their trajectories are calculated so that the spacecraft and the planet arrive at the same point at the same time. The path may look curved because both objects are moving around the Sun. A mission succeeds not because the ship chooses the correct direction once, but because its motion is shaped to match a future encounter. This is why a return trajectory cannot be created from a single straight line on a map. A line from the spacecraft to Earth's current position describes only where Earth is now. If the ship begins traveling along that line, and the journey takes months or years, Earth will be somewhere else by the time the ship reaches the region. The spacecraft could follow the direction perfectly and still miss home completely. That sounds simple in theory. Astronomers can predict Earth's orbit with extraordinary accuracy. The motion of the planets is among the best understood systems in nature. But too late, the same problem appears on the other side. Even an error of a few hours can become severe when the ship is moving at interplanetary or interstellar speed. The return corridor is not simply a wide region near the Sun. It is a narrow appointment with a planet moving continuously along a curved path. This gives the return a quiet tension that grows with distance. At first, a small correction may seem unimportant, a fraction of a degree, a slight error in velocity, an engine burn that ends a little early. But time gives these errors room to grow. The spacecraft continues traveling, and the difference between the intended path and the real path becomes larger. Nothing outside the window would reveal the error. Deep space would remain dark. The sun might slowly brighten ahead. Familiar stars might shift almost imperceptibly. The navigation display could show the difference, but the human eye would not. The spacecraft could travel millions of kilometers along the wrong approach, while everything still looked calm. Each correction changes where the ship will arrive. Each engine burn changes the timing. Each new observation refines the estimate. The spacecraft must repeatedly compare where it believes it is with where it truly is, then compare both with where Earth will be. A return path is therefore not a fixed road created at the beginning. It is a moving calculation that must remain alive throughout the journey. This can happen even when the ship is not visibly damaged. A failed sensor may make position uncertain. A star tracker may lose accuracy. A communication system may stop receiving updated data from Earth. An engine may produce slightly less thrust than expected. A leak may change the spacecraft's mass or rotation. Each problem seems small, alone, but deep space gives small problems time. The moving Earth also creates a challenge near the end of the journey. Returning to the solar system is not the same as returning to the planet. The ship might enter the region where the planets orbit and still be separated from Earth by hundreds of millions of kilometers. If Earth is on the far side of the Sun, the crew may need to remain in a solar orbit and wait for a better meeting. The ship would need to slow enough to remain near the Sun rather than passing straight through. It would need to shape an orbit that eventually intersects Earth's path. It would need to survive the additional time. The closer the spacecraft comes to home, the more the simple idea of arrival breaks into new stages. This is where Earth becomes more than a moving target. It becomes a moving target with its own velocity. A spacecraft cannot safely meet the planet by arriving at the same point while traveling in a completely different direction or at an extreme speed. It must approach in a way that allows capture, orbit, docking, or entry. A ship crossing Earth's orbit at enormous speed might pass near the planet for only moments. If it cannot slow down, Earth's gravity may bend the path without holding it. The crew could see home grow large through the windows, and then watch it shrink again behind them. They would have reached the correct region, perhaps even passed close enough to photograph oceans, and still failed to return. That possibility reveals the full meaning of interception. To return, the ship must not only find Earth's future location, it must arrive with a compatible motion. Its trajectory has to be shaped so that the difference between its velocity and Earth's velocity can be removed. Otherwise, the meeting becomes a flyby. This is why orbital missions spend so much effort controlling speed. Reaching Mars is not enough if the spacecraft cannot slow into orbit. Reaching Jupiter is not enough if the mission requires remaining nearby. The same principle becomes even more severe for Earth return. The crew cannot simply cross the planet's path. They must become part of the motion of the Earth system again. And all of it begins with accepting that Earth is not waiting in the place it was left. The planet has continued its journey without the spacecraft. Seasons have changed. Continents have rotated through daylight and darkness. The moon has completed countless orbits. The sun has moved among the stars. Human lives have continued beneath the atmosphere. This gives the return another emotional weight. Even if the spacecraft reaches Earth perfectly, the world waiting there may not be the world the crew remembers. Years or decades may have passed. People may have aged. Cities may have changed. The physical planet may be the same home, but the human home may have moved forward. That is not a navigation problem, but distance creates it. A long return stretches the separation until home becomes partly memory. The planet can be intercepted, the past cannot. Every day of travel carries the crew closer to Earth's future and farther from the Earth they left. This is the quiet truth beneath the calculations. Spaceflight can sometimes return a body to the place it began, but it cannot return the traveler to the same moment. The longer the distance, the more the difference matters. A mission lasting months returns to a changed season. A mission lasting years returns to changed lives. A mission lasting generations would return strangers to a world remembered only through records. This does not make navigation meaningless. It makes successful return even more remarkable. To bring a spacecraft back from deep space would require predicting the motion of a planet, controlling the motion of a ship, surviving the delay between them, and accepting the time that has passed. It would be a meeting between two journeys, Earth continuing around the Sun and the spacecraft attempting to rejoin it. A perfect prediction of Earth's orbit solves only half of the meeting. The spacecraft must still reshape its own motion so that the two paths cross correctly. A map can describe where home will be, but it cannot provide the speed, fuel, or control needed to arrive there. The target may be understood with great precision, while the traveler remains trapped inside the wrong movement. And this is why knowing where Earth will be is still not enough. The ship can predict the planet's future position perfectly and remain unable to reach it because direction and trajectory are not the same thing. That difference sounds technical, but it is one of the most human mistakes we make when imagining space. On Earth, facing a direction often feels like moving in that direction. A car turns its front wheels and follows the road. A person changes course by turning the body and taking a step. A boat points toward a harbor and uses the water beneath it to begin moving that way. The direction we face, the direction we intend to go, and the direction we actually travel usually remain close enough that the mind treats them as one thing. The hull may turn until Earth is directly ahead of the windows. The instruments may lock on to the sun. The crew may see the familiar region of the sky in front of them and feel, for a moment, that the return has begun. But unless the engines fire, the ship continues along the same trajectory it had before the turn. It is facing home while still traveling away from it. This happens because motion in space is carried forward. The ship already has a velocity, which means it has both speed and direction. That velocity does not disappear when the ship rotates. Rotation changes the orientation of the vehicle, not the movement of its center through space. The spacecraft can spin slowly, point sideways, or face backward, while its overall path continues almost unchanged. This becomes easier to understand if we imagine a ball thrown across a room. While the ball is flying, painting an arrow on its surface would not change where it lands. The arrow could point left, right, backward, or down. The ball would still follow the motion given to it when it was thrown. A spacecraft in deep space behaves in the same general way, except the scale is far larger and the motion may continue for years. That distinction is the heart of spaceflight. To alter a trajectory, the ship must accelerate. It must add velocity in one direction, remove velocity in another, or combine both changes into a new path. Every engine burn is a deliberate adjustment to motion. Some burns are small, correcting a tiny error. Others are large enough to reshape the entire mission. But no amount of turning the hull can replace the need for force. Suppose the spacecraft is traveling outward at a high speed. It has spent months or years building distance from the sun. Its trajectory may be carrying it across the solar system or toward interstellar space. The crew turns the ship so the engines now point in the direction of travel. When the engines fire, the ship begins to slow relative to that outward motion. At first, the spacecraft is still moving away from Earth, only less quickly than before. The engines may burn for minutes, hours, days, or much longer depending on the propulsion system and the required change. During that entire time, the ship can be pointed home in one sense, while still increasing its distance from home. Only after enough outward velocity has been removed does the ship reach the moment when it is no longer moving farther away along that part of its path. Then, additional acceleration can begin building speed back toward the inner solar system. The return is therefore not a single turn. It is a long process of cancelling one journey before creating another. Spaceflight often depends on a quantity called delta V, a way of describing how much a spacecraft can change its velocity. The term may sound dry, but it represents something simple and severe: how much power the ship has to rewrite its future path. A spacecraft with enough delta V can slow, turn, enter orbit, leave orbit, correct errors, and perhaps return. A spacecraft without enough may know exactly what it needs to do and still be trapped on its current trajectory. A ship can be relatively close and still be moving in the wrong way with no fuel to correct it. Another ship can be farther away but have a carefully designed return path and enough propulsion to complete it. What matters is not only where the spacecraft is, but how it is moving and how much that motion can still be altered. Two spacecraft can occupy nearly the same point and have completely different futures. One may be moving gently into a stable orbit. The other may be racing past too quickly to remain. One may have enough fuel to match Earth's path. The other may have only enough to change its direction slightly before continuing into darkness. Their positions may look similar on a diagram, while their trajectories make one return possible and the other impossible. This is especially important because Earth is already moving quickly around the Sun. Returning does not mean reducing the spacecraft's speed to zero. There is no universal stop point waiting in space. The ship must match the motion of the system it wants to rejoin. It must arrive with the correct speed and direction relative to Earth, the Sun, or whatever orbit it plans to enter. If the ship somehow removed all of its motion relative to one distant set of stars, Earth would still be moving around the Sun, and the Sun would still be moving through the galaxy. The spacecraft would not be waiting calmly for home. It would be left behind as the solar system continued onward. There is no single state called standing still that makes the return easy. That can feel unsettling because the human body depends on fixed surroundings. We feel still while sitting in a room, even though Earth is rotating, orbiting the Sun, and traveling through the galaxy. The walls, air, ground, and everything nearby share almost the same motion, so stillness becomes a local experience. We do not feel the larger movement because we are carried inside it. This is why a trajectory is not just a line pointing toward a destination. It is a complete description of how the ship will move through time. It includes the speed, direction, gravitational forces, engine burns, and future encounters that shape the route. A line drawn from the ship to Earth may look direct, but the most efficient or even possible path may curve around the Sun, use gravity, or approach from an angle that seems unrelated to a simple backward route. A spacecraft returning from the outer solar system might aim ahead of Earth, behind Earth, or toward a point that appears empty. It may first enter a solar orbit, complete part of that orbit, and meet Earth later. It may need to pass near another planet to change speed. It may need to approach the Sun before turning outward again. The path that leads home could briefly carry the ship in a direction that seems to move away from home. We expect progress to look like decreasing distance. But in space, a temporary increase in distance can be part of a successful return. The ship may need to shape its orbit before the meeting becomes possible. A direct line may require more energy than the spacecraft has, while a longer curved path may use gravity and timing more efficiently. This is another reason deep space return depends on calculation rather than instinct. Human senses cannot feel orbital geometry. The crew may see Earth in one direction, while the correct engine burn points somewhere else. They may feel as though they are turning away from the planet when the navigation system is actually placing them on the only route that can intercept it. That would be difficult even if every system worked perfectly. In an emergency, it becomes worse. A damaged engine may produce uneven thrust. A failed control system may make the ship harder to orient. A fuel leak may change the mass. A broken sensor may weaken the estimate of position and velocity. The crew may still know which star is the sun, yet lack the precision needed to shape a return trajectory. This creates a quiet form of helplessness. The crew may not be lost in the ordinary sense. They may have star maps, accurate clocks, navigation records, and clear knowledge of Earth's future position. They may be able to point at home whenever they wish. But the ability to point becomes almost meaningless without the ability to change motion. The spacecraft's existing velocity may be enormous compared with the small corrections it can still make. Imagine a ship moving sideways relative to Earth while trying to return. The engines may push toward the planet, but the sideways motion remains. The result is not a straight approach. It is a diagonal path, a combination of old velocity and new acceleration. This is similar to crossing a fast river. A swimmer who points directly toward the opposite bank may be carried downstream. To arrive at a chosen point, the swimmer aims upstream, allowing the current and the swimming motion to combine. In space, the current is the spacecraft's own existing velocity, along with the gravitational movement of the system around it. The ship may need to aim away from Earth in order for the final trajectory to meet Earth later. There is no visible downstream. There is no sound of current. The ship's motion may be impossible to sense from inside. The crew can float in apparent stillness while the spacecraft travels tens of thousands of kilometers every hour. Only instruments reveal the true path. This lack of physical feeling can make trajectory errors emotionally difficult to grasp. If a ship begins drifting from its planned route, nothing may tilt, nothing may shake. There may be no sensation of turning. The stars outside can look almost unchanged. Yet the mathematical future of the spacecraft may be moving farther from Earth with every second. That is why deep space missions depend on constant tracking. Signals from the spacecraft are measured from Earth. The slight change in frequency can reveal motion. The timing of radio communication can help estimate distance. Star trackers determine orientation. Gyroscopes and onboard sensors monitor rotation. Each system contributes to a picture of where the spacecraft is going, not simply where it is pointing. If the ship believes it has one velocity, but actually has another, a perfectly executed burn can produce the wrong trajectory. The engine may work exactly as commanded and still send the spacecraft past Earth. Precision in thrust is useless when the starting information is wrong. The answers may be extremely accurate, but never infinitely exact. Over a short journey, small uncertainties remain small. Over deep space distances, they can widen into millions of kilometers. Corrections keep the prediction alive, but corrections consume resources. Every burn uses fuel. Every maneuver adds stress. Every new calculation depends on sensors and communication. A spacecraft built for an outward journey may have enough reserve for ordinary course changes, but not create freedom. That thought becomes more severe the farther the ship travels. Near Earth, rescue, docking, and frequent corrections may still be possible. Farther out, every maneuver must be planned carefully. Deep in space, the ship may carry only enough propulsion to maintain attitude, protect instruments, or make tiny adjustments. The main trajectory may be effectively fixed. The spacecraft can turn its antenna toward Earth. It can send a message. It can orient a camera toward the fading sun. It can remember the direction of home. But its center of mass continues along a path that no visual turn can undo. This is why deep space can be so emotionally cold. It does not hide Earth. It does not erase the maps. It may allow the crew to know exactly where home is. The cruelty comes from making that knowledge insufficient. The correct direction can remain available long after the correct motion has become impossible. And even if the engines can still change the trajectory, the amount of change required may be enormous. The outward velocity must be cancelled. Sideways motion must be corrected. A new path must be created to intercept the moving Earth. Speed must later be removed again near arrival. Every stage asks for more energy, more fuel, and more time. And once that difference is fully understood, the true cost of turning back begins to appear. That speed may have taken years to build, a series of engine burns to create, or the gravity of planets to provide. It may be the reason the mission could travel so far in the first place. But the moment the crew decides to return, the same speed that once made the mission possible becomes something that must be removed. This is the quiet cruelty of velocity. Accelerating away from Earth creates a future obligation. If the spacecraft is ever expected to come home, the speed gained on departure must eventually be cancelled, reshaped, and then reduced again near arrival. The outward journey is not one half of the trip in any simple sense. It is the creation of a physical problem that the return must solve. A spacecraft moving quickly through deep space carries no visible sign of this burden. There is no wind against the hull. No engine noise is required to maintain speed. Inside, the crew may float in silence while the ship crosses enormous distances. The motion feels free because no fuel is being burned to continue it. To change the trajectory, the engines must produce thrust. That thrust must act long enough to remove the spacecraft's outward velocity. If the ship is traveling at tens of thousands of kilometers per hour, a small engine burn will not turn it around. It will only change the path slightly. The craft may begin curving toward home while still moving mostly away. This is why a ship can rotate in minutes and still require months to reverse course. The hull is light enough to turn with small control thrusters, but the entire spacecraft is carrying momentum. Every tank, wall, engine, instrument, supply container, and human body on board shares the same motion. Reversing it means accelerating all of that mass in a new direction. A crewed spacecraft needs shielding, life support, water, food, power systems, spare parts, living space, communications, navigation equipment, and propulsion. If the mission is meant to last years, the vehicle may be closer to a small moving habitat than a simple capsule. Everything added for survival also becomes something the engines must slow, turn, and accelerate again. The relationship between fuel and mass creates one of the hardest problems in rocketry. More fuel allows a spacecraft to change velocity more, but fuel itself has mass. Carrying extra fuel requires more energy to accelerate the fuel along with the rest of the ship. Larger tanks require stronger structures. Stronger structures add more mass. More mass demands more fuel. This is why spacecraft cannot carry unlimited reserves for every possible emergency. A vehicle designed to reverse from any point in a deep space journey would need enough propulsion not only to cancel its outward speed, but to build return speed, make corrections, slow near the sun, meet Earth, and survive the final approach. The amount of fuel required could make the original launch nearly impossible. This may feel obvious, yet it changes the emotional meaning of departure. When a mission leaves Earth, the ability to come home is not a permanent promise. It is a resource built into the vehicle. Every maneuver can reduce it. Every unexpected correction can consume part of it. Every decision to travel farther can move the ship closer to a point where return is no longer supported by the fuel remaining on board. A crew could pass the point of safe return while everything still appears normal. The engines may be healthy. Earth may still respond to radio messages. The ship may have enough fuel to continue toward its destination. But the amount required to reverse, return, and slow down may already exceed what remains. This is not because the spacecraft has run out of fuel completely. It may still have enough for attitude control, course corrections, or arrival at the planned destination. The danger comes from the size of the return maneuver. A deep space reversal demands much more than ordinary navigation. It asks the spacecraft to perform a second launch without a planet, without a launch pad, and without new propellant. Consider a ship moving outward from the Sun. To return efficiently, it must first reduce the velocity carrying it away. Depending on the path, it may need to fire its engines opposite its motion for a long time. Once that outward speed is cancelled, the ship must continue accelerating inward so that the return does not take an unbearable amount of time. The spacecraft has spent fuel building speed toward home. That speed now has to be removed before the ship can remain near Earth. If it arrives too fast, it may pass through the system, miss the planet, or face an entry velocity the vehicle cannot survive. The return, therefore, requires energy at both ends. First to begin coming home, and later to stop coming home too quickly. This creates a balance that mission planners must think about before launch. A faster ship shortens the journey, reducing the time the crew spends exposed to radiation, isolation, equipment failure, and limited supplies. But greater speed increases the difficulty of slowing down. A slower return may save fuel, yet it asks the spacecraft and its passengers to survive for much longer. This is why the cost of turning back is not only fuel, it is also time, mechanical life, risk, and opportunity. A long engine burn wears propulsion systems that may never have been intended for continuous use. Pumps, valves, cooling systems, and power supplies must work far beyond their original plan. If one component fails during the reversal, the spacecraft may be left with less fuel and an even worse trajectory. The ship may lose enough outward speed to abandon its original mission, yet fail to gain enough inward speed to return. It could enter a long, empty orbit around the Sun or drift into a region where neither destination is reachable. The decision to go home may close the route forward before it successfully opens the route back. The crew would need confidence not only that the engines can start, but that they can complete the entire sequence. Fuel calculations would have to include reserves for uncertainty. Thrust may be slightly lower than expected. A burn may need to last longer. The ship may require additional course corrections. The planned path may change as new measurements reveal small errors. The spacecraft's mass may also change during the journey. Food is used, waste is stored or released, fuel is consumed. Equipment may be moved. Small leaks can alter the balance. A vehicle that responds one way at departure may respond differently years later. The engines must push the remaining mass with enough precision to create the correct trajectory. If the propulsion is powerful, the burn may be shorter but place greater stress on the vehicle and crew. If the propulsion is gentle, the engines may need to operate for weeks or months. Low-thrust systems can produce large changes over time, but they require patience and functioning equipment. During the slow turn, the ship continues traveling along a path that is only gradually becoming safer. That would be difficult to accept emotionally. The engines are firing toward home. Fuel is disappearing. The ship vibrates with effort. Yet Earth remains farther away at the end of each day. The spacecraft is not failing. It is paying off the velocity of the outward journey. This is unlike travel on Earth, where a traveler who turns around usually sees immediate progress back toward the starting point. In deep space, the first part of returning may look almost identical to continuing away. The only evidence of change exists inside the instruments. A smaller outward velocity, a slightly altered future path, a predicted meeting point that moves closer to Earth. Propulsion systems are not timeless. Chemical engines may have limited restart capability. Electric propulsion may depend on power systems that weaken with age or distance from the Sun. Nuclear systems may degrade. Fuel lines can freeze. Valves can stick, and materials can become brittle after years of radiation and temperature changes. A failed ignition would not create an explosion in every case. It might produce something quieter, no thrust, an incomplete burn, a warning signal, and the realization that the planned route no longer exists. The crew could know exactly how much velocity needed to change while having no working way to change it. This calmness is part of what makes the situation so unsettling. The cost of turning back does not always appear as danger outside the window. It appears as numbers declining on a display: remaining propellant, engine temperature, power output, predicted arrival speed, life support duration. Each value may look manageable alone, yet together they determine whether home is physically reachable. This is why the most dangerous part of a deep space return may be the need to plan the entire journey before committing to the first burn. The spacecraft cannot solve only the immediate problem of turning inward. It must preserve enough capability for every later stage. A maneuver that points the ship perfectly toward Earth can still be fatal if it leaves no reserve for arrival. That is the real price of distance. It does not merely create a longer journey, it multiplies every requirement. More time demands more supplies. More supplies add mass. More mass demands more fuel. More fuel adds still more mass. Greater speed saves time, but increases the braking requirement. Slower speed reduces propulsion needs, but extends exposure and equipment use. This is why deep space missions are usually designed around commitment. Robotic probes may not carry a return system because the mass would reduce what they can accomplish. Human missions would require more caution, but even they could cross distances where complete return becomes impractical. The ability to continue may remain long after the ability to reverse has disappeared. A spacecraft moving through deep space may carry many possible small trajectories within its remaining fuel. It can adjust course, avoid a hazard, turn an antenna, or refine an approach. But a complete return is not a small possibility. It is an enormous rewrite of motion, often larger than everything the ship was designed to do after departure. At some point, the cost of turning back becomes larger than the resources remaining on board. The exact point depends on speed, mass, propulsion, distance, and the geometry of the solar system. It may not be marked on any chart, yet it is as real as a wall. This is where the dream of reversal meets the design of the spacecraft. A vehicle may survive the dark, know the correct direction, and understand the entire path. None of that creates propellant. None of it repairs an engine. None of it removes the velocity already carried into deep space. And once the full cost of reversing course is counted, the next problem becomes impossible to ignore. The fuel needed for home may already be gone. The tanks may still contain propellant. The engines may still be able to fire. The spacecraft may still have enough fuel to rotate, correct its attitude, adjust an antenna, avoid a small hazard, or refine its path toward the destination ahead. From inside the ship, nothing has to feel empty. But the fuel required to return is not the same as the fuel required to continue. A spacecraft can remain operational long after it has lost the ability to come home. This difference begins at launch. Every mission carries fuel for specific tasks: leaving Earth, escaping an orbit, accelerating toward a destination, adjusting the trajectory, slowing near arrival, and keeping some reserve for uncertainty. Those reserves are never infinite. They are calculated around a planned journey, a planned duration, and a planned sequence of maneuvers. Deep space travel does not offer a place to refill what has been spent. There are no stations waiting between the planets, no tankers hidden beyond the sun, and no easy way to gather useful propellant from the emptiness around the ship. Whatever leaves Earth with the spacecraft must support every later change in motion, unless the mission reaches a destination where new resources can somehow be produced. A ship that turns back late may discover that the return was consumed little by little, without anyone noticing a single dramatic moment. Each event may use only a small part of the reserve, but the reserve is the part of the spacecraft's future that has not yet been assigned. Once it is spent, the options it supported disappear with it. This is one of the deepest differences between a machine on Earth and a machine in deep space. On Earth, fuel can often be replaced. A vehicle can stop, wait, repair, and continue. In space, fuel is not simply energy for movement. It is the ability to choose a different trajectory. When the propellant is gone, the spacecraft does not stop. It continues moving along the trajectory it already has. That is what makes fuel loss so strange in space. Running out does not look like a vehicle slowing to a halt beside a road. It looks like motion becoming permanent. A crew could still see the sun. They could still know where Earth will be. They could still receive messages and calculate the exact path home. Yet, if the required velocity change is larger than the remaining fuel can provide, the calculation becomes a description of something they cannot do. This can happen even when the fuel gauges do not read zero. A ship may have 20% of its propellant left and still be unable to return if the journey requires 30%. It may have enough fuel to begin the reversal, but not enough to finish it. It may have enough to reach the inner solar system, but not enough to slow down near Earth. That work becomes harder because the spacecraft must carry its fuel while using it. Propellant has mass. Tanks have mass. The engines have to accelerate not only the crew and equipment, but also the fuel reserved for later burns. At the beginning of a maneuver, the ship is pushing everything it will eventually spend. This is why doubling the distance does not simply double the fuel requirement. The relationship can become much worse, especially when the spacecraft must accelerate, reverse, and brake several times. More fuel makes the vehicle heavier, and a heavier vehicle needs still more fuel to create the same change in velocity. Mission designers reduce this burden by choosing efficient routes, using gravity assists, accepting long travel times, and avoiding unnecessary maneuvers. Robotic probes can be made light because they do not need air, food, living space, or heavy protection for human bodies. A crewed ship would carry far more mass, and every additional system would make the return more expensive. The systems that keep the crew alive for years become the same mass that must be slowed, redirected, and accelerated back toward Earth. This creates an uncomfortable trade. Carrying more supplies allows the crew to survive a longer return, but the extra mass demands more propulsion. Carrying less mass improves the ship's ability to change course, but leaves less time for the people on board. A mission may therefore be designed around a point of no practical return. Before that point, enough propellant and supplies remain for the ship to reverse. Beyond it, the planned destination may still be reachable, but Earth is not. The exact boundary can shift as fuel is used and conditions change. Yet it is real even if no light appears on the control panel. There is no wall in space, but the fuel calculation creates one. This wall is not defined only by distance. A spacecraft moving slowly might remain capable of return from farther away. A faster ship may lose that ability sooner because more velocity must be cancelled. A damaged engine can move the boundary closer. A fuel leak can move it suddenly. A failed navigation burn can consume the margin that once made return possible. That relationship can become dangerous in ways the crew cannot easily feel. Fuel levels are visible, but future needs are estimates. Engineers must predict how much propellant will be required for burns that may happen months or years later. They must include uncertainty in engine performance, navigation accuracy, and the actual path the spacecraft will follow. This is why margins are so important. A mission does not normally plan to use every final drop. Some propellant remains for course corrections, unexpected delays, or imperfect engine burns. But emergencies consume margins quickly because they create tasks the original mission never included. The spacecraft may have been designed to slow at a distant destination using an atmosphere, a planet's gravity, or infrastructure waiting there. A return to Earth may require a very different sequence. The vehicle may have enough fuel for the planned arrival, but not enough for the path home. That is not necessarily a design failure. Carrying the extra propellant for every possible reversal could make the mission impossible to launch. Spacecraft are built around priorities. Some have a way home, some do not. Some can return only during an early part of the journey. Some become one-way machines the moment they leave Earth. Even when the ship has a return plan, fuel can be lost through small imperfections. Engines do not always produce exactly the predicted thrust. A burn that is slightly weak must last longer. A burn that begins late may require more correction later. A small misalignment wastes part of the thrust in the wrong direction. This makes precision a form of fuel conservation. A perfectly aimed burn uses the available propellant efficiently. A small error spends part of the reserve without creating the intended motion. Over a long journey, repeated imperfections can quietly remove the margin needed near Earth. Leaks create another kind of uncertainty. A major rupture would be obvious, but a slow leak can continue for months. Propellant may escape gradually into space, too little at a time to create a dramatic event. The loss may be measured and understood, yet the crew can do nothing except watch the return options shrink. Some propellants must also be stored under demanding conditions. Cryogenic fuels can slowly boil away if they are not perfectly insulated and cooled. Other systems depend on pressure, temperature, and seals that must remain reliable for years. A return burn planned far in the future assumes that the fuel will still be usable when the time comes. This is why usable fuel is more than a number. It is an entire system: tanks, pumps, valves, power, cooling, controls, and engines. The return depends on all of them working together after a long exposure to radiation, vacuum, temperature changes, and mechanical aging. The crew may try to conserve what remains. Non-essential maneuvers can be cancelled. The ship can rotate using smaller thrusters or reaction wheels. Power can be reduced. The planned route can be adjusted to use gravity where possible. Every small saving may extend the range of choices. This leads to difficult decisions. A course correction now may prevent a much larger correction later, but it consumes fuel immediately. Waiting may preserve the reserve, yet allow the error to grow. The crew must decide how much certainty to buy with a resource that cannot be replaced. The problem becomes more severe because a spacecraft cannot use all its remaining propellant for one burn. Some must be kept for orientation, communication, thermal control, and final approach. If every drop is spent accelerating toward Earth, the crew may lose the ability to point the antenna, align the ship, or correct the arrival. A ship that reaches Earth with no control authority may still fail to come home. It might pass at the wrong angle, enter the atmosphere incorrectly, or lose communication during the final approach. The return plan must preserve enough propellant not just to arrive, but to remain controllable until the journey is over. Early in the mission, a small burn changes the path gradually over a long distance. Near Earth, a small burn can decide whether the spacecraft enters the correct corridor or misses it completely. The crew may therefore have to protect a reserve they desperately want to use sooner. This gives every maneuver a second meaning. An engine burn is not only a change in the present path, it is a reduction in the number of changes still possible. The ship gains one correction and loses part of every future correction. At some point, the remaining propellant becomes so limited that only small adjustments are possible. The main trajectory is effectively fixed. The ship may still steer its instruments and send signals, but it can no longer create the large velocity change required for Earth. That may be the coldest form of being stranded. The crew does not need to search for a hidden planet. They do not need to solve a mystery. They can know the exact location of Earth and the exact maneuver that would bring them back. There is no natural force that will notice the shortage and carry them home. Gravity will continue shaping the trajectory according to the ship's position and speed. The spacecraft will keep moving even after the last useful reserve has been protected for communication or attitude control. This is why an empty return reserve is more final than it appears. The engines may fire again, but not strongly enough. The ship may bend its path, but not far enough. Earth may grow closer in one calculation and remain unreachable in another. The distance is no longer the only barrier. And once the reserve becomes too small, every remaining maneuver must be almost perfect, because the smallest error may consume the last chance to reach home. Near Earth, a small mistake can often be seen quickly. A spacecraft drifts from its planned path. Tracking stations notice the change, and a correction is made before the difference becomes serious. The distance is manageable. Communication is fast. The engines still have room to respond. A tiny change in direction does not remain tiny. The spacecraft continues moving, and the error continues moving with it. At first, the difference may be no more than a few kilometers. Then hundreds. Then thousands. Over months or years, a fraction of a degree can become a separation large enough to miss a planet completely. This is one of the hardest ideas to feel from inside a spacecraft. The crew may see no sign of danger. The stars outside the windows appear almost unchanged. The ship does not lean, slide, or shake. There is no road beneath it showing that the vehicle has crossed a line. Yet the future path may already be opening away from Earth. A spacecraft traveling through deep space can move tens of thousands of kilometers every hour. At that speed, an angle too small for the human eye to notice can send the ship across an enormous distance. The longer the journey continues, the more space the error has to grow. That requires knowing the spacecraft's position and velocity with extraordinary precision. Where exactly is the ship? How fast is it moving? In which direction? How much did the last engine burn change the path? How are the sun and planets bending the trajectory? What small forces are acting on the hull? No measurement is perfect. A radio signal may reveal distance, but only within a margin. A star tracker may determine orientation, but not with infinite accuracy. An engine may be commanded to burn for a precise amount of time, yet produce slightly more or less thrust than expected. A valve may open a fraction late. The spacecraft's mass may differ from the model. Imagine a burn intended to change velocity by a very exact amount. The engines fire, the ship responds, and the maneuver appears successful. But the thrust was slightly weaker than predicted. The difference may be so small that the crew feels nothing, and the instruments show only a minor deviation. The spacecraft crosses space along a path that is almost correct. That word, almost, becomes more dangerous with every passing day. The ship may still be moving toward the inner solar system. The Sunday may still brighten ahead. Earth's future orbit may still appear close on a navigation display. A planet is large by human standards and very small compared with the distances around it. Earth is only one moving sphere inside an orbit hundreds of millions of kilometers wide. A returning spacecraft must reach the right part of that orbit at the right time. Missing by a tiny fraction of the overall journey can still mean missing the planet entirely. The spacecraft is predicted to pass through a region of possible positions. New measurements narrow that region. Course corrections move it. Uncertainty slowly widens it again. The return remains safe only while Earth lies inside the future corridor, and the ship still has enough control to adjust. A large reserve allows repeated corrections. A nearly empty reserve does not. The crew must decide when an error is real enough to justify spending propellant. Correct too early, and they may respond to a measurement that later proves inaccurate. Wait too long, and the correction may become much larger. This creates a slow tension between certainty and time. The crew wants more observations before acting, but the spacecraft keeps moving while those observations are collected. A small uncertainty today may become a large maneuver tomorrow. Yet burning fuel on the wrong assumption can be just as dangerous. A spacecraft with abundant fuel can treat uncertainty as an inconvenience. A stranded ship cannot. Each correction has to justify itself. Each engine burn must produce exactly the intended result. The crew may reach a point where the vehicle can survive only one more meaningful maneuver. This does not mean the machinery must fail dramatically. The burn could be completed almost perfectly and still leave the spacecraft outside the narrow return corridor. A tiny difference in angle, duration, or thrust can decide whether the ship meets Earth or passes through empty space nearby. A miss of several thousand kilometers sounds small beside the scale of the solar system, but it can place the spacecraft beyond any practical help. Earth's gravity may not capture it. The ship may not have enough fuel to turn back after the flyby. The planet could pass across the sky as a distant blue object, visible but unreachable. The same problem affects timing. A spacecraft can travel through the correct point in space and still miss Earth because it arrives too early or too late. The planet continues moving along its orbit. The target is not only a location but a moment. If the ship is slightly faster than planned, it reaches the meeting point early. If it is slower, Earth may already have passed. A difference measured in seconds during an engine burn can become hours or days at arrival. This is why mission control does not wait until the spacecraft is visibly off course. The future miss is calculated long before it occurs. Engineers compare the predicted trajectory with the desired one, searching for small differences that will become large later. That future position may be years away and impossible to observe directly. It exists only inside models, measurements, and probability. A successful return depends on trusting those calculations enough to spend irreplaceable fuel. A system that once measured orientation perfectly may begin reporting a slight bias. If the bias is not recognized, every later calculation inherits it. That may be more dangerous than a clear failure. A broken sensor can be ignored or replaced. A sensor that appears healthy but gives slightly incorrect data can guide the spacecraft away from Earth. While every maneuver seems reasonable, a position estimate is slightly wrong. The planned burn is therefore slightly wrong. The engine performs slightly below expectation. The next position estimate assumes the previous burn worked exactly. Each difference is small, but together they move the spacecraft farther from the intended path. This is why independent systems are so valuable. Star trackers can be compared with gyroscopes. Radio measurements from Earth can be compared with onboard navigation. Different sensors can reveal when one begins to drift. Redundancy allows the spacecraft to question its own. The ship may be correctly aimed for months without anything outside looking different. It may also be drifting toward failure with the same silence. This silence can make a developing error feel unreal. On Earth, danger often becomes louder as it approaches. A vehicle vibrates. A storm appears. A road narrows. In deep space, a fatal miss can develop without any new sound, motion, or image. By the time Earth is large enough to see clearly, many corrections may already be impossible. The ship is moving too quickly, the remaining distance is too short, and the fuel reserve is too small. A late maneuver requires more force because there is less time for a small change to influence the path. A tiny burn months in advance can move the arrival point by thousands of kilometers. The same correction attempted hours before arrival may require far more fuel. This is why waiting for visual certainty can be fatal. This becomes especially difficult when the spacecraft is damaged or communication with Earth is weak. The people on board may have incomplete data. Mission control may have a different estimate. Signals take time to travel, so the two sides may not even be discussing the same state of the ship. This is where the problem of small errors begins to merge with the problem of delayed communication. Earth can calculate a correction with extraordinary care, but distance prevents that correction from arriving instantly. The farther the spacecraft travels, the more every instruction describes a past that no longer exists. If the return margin is wide, the delay can be managed. If the margin is narrow, the guidance may arrive too late to help. The ship must increasingly rely on its own systems and crew. Even when Earth has better computers, more specialists, and a clearer view of the entire mission, that separation becomes more severe as the fuel reserve shrinks. There may be time for only one correction, and the crew cannot wait days for confirmation. They must act using the best information available on board. If they are wrong, Earth may learn about the mistake only after the chance to repair it has passed. This is why a small mistake in deep space is never only about accuracy. It is also about timing, communication, and the ability to respond before the geometry becomes fixed. The error itself may be tiny, but the system surrounding it is slow. A signal can travel no faster than light, and even light becomes slow across the distances of deep space. Close to Earth, the delay feels almost non-existent. Far beyond the planets, it becomes part of the mission. Every command, warning, and update must cross the same darkness the ship is trying to escape. And once every correction depends on information arriving from an increasingly distant past, the return begins to face another quiet limit. Earth's instructions may always come too late. A spacecraft near Earth can send a message and receive a reply quickly enough that communication still feels immediate. Mission Control watches the data, gives instructions, and the crew responds. The distance is real, but it does not yet dominate the conversation. A signal from the ship crosses the darkness at the speed of light, reaches Earth, is received, studied, and answered. Then, the reply begins the same journey back. Even when the people on both sides respond without hesitation, the distance has already placed a pause between them. Near the Moon, the delay is small enough to manage almost like an ordinary conversation. Near Mars, it can stretch across many minutes in each direction. Beyond the outer planets, the wait becomes hours. A spacecraft far beyond the solar system could send a message and hear nothing back for days, months, or much longer. This is not a problem technology can simply remove. Antennas can become larger, signals can become stronger, computers can process information faster. But none of these can make information travel faster than light. The delay is not caused by weak equipment. It is built into the distance itself. For a return journey, this changes the meaning of mission control. Earth may remain the center of knowledge, with large teams of engineers, complete records, detailed models, and powerful computers. But knowledge is useful only if it reaches the spacecraft while action is still possible. Suppose the ship detects a navigation problem. The crew sends its measurements to Earth and waits. By the time Mission Control receives them, the spacecraft has already moved far beyond the position described in the message. Engineers calculate a correction, test it, and transmit the instructions back. This does not mean the instructions are automatically wrong. Good navigation models can predict how the spacecraft has moved during the delay. Earth can account for that movement and send commands designed for the future. But every prediction depends on the assumption that nothing unexpected happens while the message is traveling. This turns communication into a careful exchange of predictions rather than a conversation about the present. The ship reports what has already happened. Earth answers for what it believes will happen next. Both sides are working across a gap that can never be closed. For the crew, that separation would feel very different from ordinary isolation. Earth is not silent because no one is listening. People may be watching every signal, studying every number, and preparing every possible response. Yet the spacecraft still has to wait inside the problem. If a malfunction develops quickly, the crew must act alone. They cannot describe the problem, wait for specialists on Earth, receive a complete plan, and then begin. The round-trip delay may be longer than the time available. By the time help arrives, the system may already be damaged beyond repair. The crew needs training broad enough to solve problems without immediate guidance. The onboard computers need enough information to diagnose failures, plan maneuvers, and protect the ship independently. Procedures must anticipate situations no one can fully predict. This becomes especially serious when navigation margins are small. A correction may need to happen at a precise moment. An engine burn started too late could require far more fuel or fail to shape the path correctly. If the crew waits for confirmation from Earth, the best opportunity may disappear during the silence. The crew may receive an instruction after they have already made a different decision. Earth's message might recommend delaying a maneuver the crew completed hours earlier, or it might tell them to burn the engines immediately when the ship no longer has enough fuel to do so. This affects even simple questions. When Earth asks for the current fuel level, the answer it receives is already old. When Mission Control sends a new estimate, the crew receives a conclusion based on an earlier state of the ship. The farther the distance grows, the more every piece of information must be labeled with time. There may be moments when Mission Control knows something the crew does not. A pattern in the data may reveal a failing component. Engineers send a warning, but the signal still has to cross the distance. During that journey, the crew continues using the system, unaware that every operation may be making the failure worse. The opposite can also happen. The crew may repair a problem and send confirmation, while Earth spends hours or days believing the spacecraft is still in danger. Mission Control cannot know the outcome until the signal returns. People on Earth may watch an old crisis unfold long after it has been solved, or long after it has become fatal. That waiting may be calm from the outside. Antennas remain pointed into the sky. Computers continue listening. The spacecraft becomes a weak signal crossing an enormous distance. Then, a packet of data arrives, carrying a few moments from the past. This is the most severe meaning of delayed communication. It does not merely slow rescue. It can make rescue impossible because every event becomes history before anyone far away can respond. A final transmission could still be traveling toward Earth while the spacecraft continues silently on its path. The people at home would not yet know that the conversation had ended. This is not dramatic in the way a visible explosion is dramatic. It is quieter. The communication link may appear normal until the expected reply fails to arrive. Even then, Mission Control cannot know immediately whether the signal was lost, the antenna turned away, the transmitter failed, or the entire spacecraft was destroyed. For the crew, the same uncertainty exists in reverse. Earth may stop responding because of a technical issue, an antenna problem, or events on the planet. The spacecraft cannot know immediately. It sends another message and waits. The silence may last longer than usual, but distance makes every pause ambiguous. A return journey cannot stop while communication is uncertain. The spacecraft still moves, fuel is still consumed, systems still age. The crew still needs to eat, sleep, repair equipment, and make decisions. The lack of an answer does not pause the mission. The ship may have to perform a major maneuver without knowing whether Earth received the plan. It may send the results and begin the next stage before Mission Control responds. Each action becomes partly irreversible before anyone at home can review it. This changes the design of the spacecraft itself. A deep space vessel cannot depend on a constant stream of commands. It needs autonomous navigation, onboard medical support, diagnostic systems, repair tools, and software capable of responding to unexpected conditions. But carrying more capability also adds mass and complexity. More computers create more possible failures. More spare parts require more storage. More systems demand more power and maintenance. Independence protects the crew from communication delay, yet makes the spacecraft harder to build and harder to keep alive. This is a pattern that appears throughout deep space return. Every protection adds weight. Every backup adds complexity. Every reserve reduces something else the mission can carry. The ship must become strong enough to survive alone, without becoming too heavy to move. No crew can train for every possible failure. No computer can contain every future problem. Deep space may expose the spacecraft to combinations of damage, aging, and human stress that no simulation predicted. When that happens, the crew may have to invent a solution using only the tools and knowledge already on board. This makes time itself part of the emergency system. Some failures develop slowly, leaving room for delayed advice. Others do not. A small leak may allow hours of calculation. A fire, loss of pressure, or critical navigation opportunity may demand action in seconds. That judgment may be made under stress, fatigue, and incomplete information. The people on board know that a better answer may be coming. They also know the ship will not wait for it. A spacecraft returning from deep space may still be under the guidance of Earth in principle. In practice, the farther it travels, the more the crew becomes its own mission control. They are no longer simply following a plan made at home. They are protecting the possibility of home with every independent choice. This last part matters because while Earth and the crew exchange messages across the distance, the spacecraft itself is changing. Components do not wait for instructions. Materials do not stop aging during the silence. Radiation does not pause while mission control studies the data. Every hour spent waiting is another hour of wear. The return journey therefore faces two clocks. One measures the time required for information to travel. The other measures how long the spacecraft can continue functioning. The first clock grows with distance. The second only moves toward failure. This is why the delay becomes more than an inconvenience. It removes the possibility of real-time rescue and leaves the spacecraft alone with every immediate danger. The ship must navigate, repair, and survive while home watches through a window into the past. And even if every message arrives, every instruction is understood, and every decision is correct, the return still depends on a machine that has been traveling through radiation, vacuum, and isolation for years. The longer this continues, the more the spacecraft becomes a world of its own. Decisions are made on board, repairs are improvised on board, and survival depends on systems that Earth can only observe after the fact. Home may still guide the mission, but it can no longer stand beside the crew when the next failure begins. And while the distance delays every answer, the ship itself begins to age, weaken, and slowly die. A seal loses flexibility. A pump begins to vibrate. A cable carries less current than it once did. A sensor reports a value that is almost correct. A filter works a little less efficiently each month. None of these changes has to look dangerous by itself. Yet together, they begin to shorten the future of the ship. Every system on board was built from materials that age. Metals expand and contract. Plastics become brittle. Lubricants change. Batteries lose capacity. Electronics accumulate damage. The vehicle may appear motionless inside the darkness, but on the microscopic level, it is always changing. This matters because a return from deep space may take longer than the outward mission was designed to last. A spacecraft built for 5 years may suddenly be asked to survive 10. A life support system sized for a planned journey may be forced to operate far beyond its intended service life. Components that were expected to be replaced on Earth may have to continue working with no replacement available. At first, maintenance may keep the decline under control. Filters can be cleaned. Parts can be replaced. Software can be reset. Leaks can be sealed. The crew can move loads, reroute power, and use backup systems. A deep space vessel would carry tools, spare parts, manuals, and perhaps machines capable of producing simple components. This is one of the quietest signs that a machine is approaching the end of its life. At launch, several systems may be able to perform the same critical function. If one fails, another takes over. But after years in deep space, the backups may already be damaged, worn, or used for other purposes. The crew may know this long before the spacecraft stops functioning. They keep records of every weak component, every reduced reserve, every repair that cannot be repeated. The ship still works, but only because certain parts have not failed yet. Radiation makes the process worse. Beyond the protection of Earth's magnetic field, energetic particles pass through the spacecraft. Shielding can reduce the exposure, but it cannot remove it completely. Electronics may experience errors. Memory can be corrupted. Sensors can degrade. Materials can slowly weaken. The crew can restart computers and replace damaged units. But every reset is a reminder that the environment outside is working against the machine. The spacecraft carries its own small island of order through a place where radiation never stops arriving. Shielding may protect the crew from much of it, yet deep space radiation remains, one of the most difficult long-term problems. Cells are damaged. The risk of illness grows. The body has to repair itself again and again while living in an environment it never evolved to survive. Weightlessness adds another pressure. Muscles weaken when they are not used against gravity. Bones lose density. Balance changes. The heart and blood vessels adapt to an environment without a clear-up or down. Exercise can reduce these effects, but it cannot make years in microgravity identical to life on Earth. This creates a difficult contrast. The spacecraft may need to take a slow, fuel-efficient route because propellant is limited. The crew may need a fast route because the body and life support systems are not designed to last indefinitely. Saving one resource places greater pressure on another. Air is even less forgiving. Oxygen must be stored, generated, or recovered through life support systems. Carbon dioxide has to be removed. Humidity must be controlled. Trace gases from equipment, materials, and human activity must not be allowed to build up. On Earth, the atmosphere surrounds every person without visible effort. Inside a spacecraft, every breath depends on power, filters, sensors, fans, and chemical systems. If one part of that chain fails, the air may slowly become unsafe even while the ship still looks normal. This is why life support cannot be treated as one system. It is a network of systems watching one another. Sensors confirm pressure, filters remove waste, fans move air, computers adjust flow. Power systems keep everything active. A failure in one place can spread into another. Power sits beneath almost every part of this network. Without energy, the spacecraft cannot move air, recycle water, control temperature, navigate, communicate, or operate most of its instruments. The source may be solar, nuclear, or some combination, but it will not remain unchanged forever. Solar panels can degrade under radiation and impacts. They also become less effective far from the sun. Nuclear power systems gradually produce less energy. Batteries lose the ability to store charge. Electrical components wear and overheat. At first, non-essential instruments are turned off. Then, lighting is reduced. Heating is limited to smaller areas. Computers operate less often. Communication windows become shorter. The spacecraft still functions, but its interior becomes quieter and darker as the available power declines. This can change the return plan. Engines that depend on electrical power may produce less thrust. Navigation instruments may be used less frequently. The antenna may not transmit as strongly. Repairs may be delayed because the equipment requires energy the ship cannot spare. Temperature control also becomes harder. Deep space is cold, but a spacecraft does not simply freeze evenly. Sunlight can heat one side, while the other radiates energy into darkness. Equipment and people create heat inside. Different sections must be warmed or cooled to keep systems within safe limits. If the thermal system weakens, fuel lines may become too cold. Electronics may overheat. and condensation may collect where it should not. Materials expand and contract as temperatures change, placing stress on joints and seals. They must remember which valve sticks, which sensor reads high, which cable overheats, and which repair can no longer be trusted. Knowledge of the ship becomes deeply personal. A new crew could read the manuals, but the people living on board understand the small sounds and habits that reveal whether the machine is healthy. Long isolation affects attention, judgment, sleep, and emotion. Repetition can dull awareness. Stress can make small problems feel larger, or serious problems easier to ignore. The return may demand careful maintenance every day for years, with no real break and no replacement crew. The spacecraft is protected by people who are being worn down by the same journey. This does not require panic or conflict. The danger can come from ordinary fatigue. A person does not need to lose control to make a mistake. They only need to be tired at the wrong moment. This is why the spacecraft's lifetime is not defined by one expiration date. Different systems approach their limits at different times. The power source may last longer than the food. The food may last longer than the water filters. The filters may last longer than the engines. The engines may remain healthy, while the crew becomes too weak to use them. The spacecraft does not need to be completely dead to become unable to return. This creates a race that is difficult to see from outside. On a map, the ship moves closer to Earth. The distance decreases. The return appears to be succeeding, but inside, the remaining lifetime of the systems may be decreasing faster than the distance. Mission planners would try to estimate these limits. They would calculate food, water, oxygen, radiation exposure, component life, power output, and medical risk. But a damaged spacecraft, returning after an unplanned reversal, is no longer following the assumptions used before launch. This uncertainty affects every choice. Using a backup system now may protect the crew, but leave no backup later. Increasing engine power may shorten the return, but stress a failing component. Reducing power may preserve the machinery while extending the journey beyond the food supply. That is why a deep space return becomes more than navigation. It becomes the management of decline. The crew is not traveling in a machine that stays constant until arrival. They are carrying a world that is slowly losing the ability to support them. There may come a point when the crew begins shutting down entire sections of the spacecraft. Empty modules are sealed. Lights are left off. Heat is concentrated in a smaller living area. Equipment is stripped for parts. The usable world contracts around them. Outside those rooms, the rest of the spacecraft still travels with them, dark and silent, carrying systems that once worked. The crew moves through a structure that is gradually becoming its own ruin. This is the quiet hope that keeps the return alive. The ship does not have to remain perfect. It only has to remain functional long enough. A damaged system can be bypassed. A failing component can be nursed through one final year. The crew can live with less comfort, less power, and less certainty. The spacecraft may reach the outer edge of the solar system and still be years from Earth. The Sunday may grow brighter, radio signals may become faster, and the familiar planets may begin appearing in navigation data. The crew could feel that home is finally near. A ship that has spent years weakening may arrive with engines that can no longer perform a major burn, shielding damaged by radiation, power reduced, and a crew physically exhausted. Reaching the solar system does not restore the vehicle. It only changes the landscape around it. The spacecraft must slow, adjust, enter the correct orbit, and meet a moving Earth. These are not gentle tasks for a dying machine. They require the very systems that have spent years being worn down by the return. This is why seeing the sun grow brighter would not mean the danger had passed. The ship could be inside the solar system and still be unable to stop. It could cross the orbit of Neptune, then Uranus, then Saturn, carrying too much speed and too little remaining life. The spacecraft has survived the silence, the delay, the fuel shortage, and the accumulating errors. But survival has only brought it to the edge of another problem. A return is not complete when the ship enters familiar space. And even if the dying spacecraft reaches the solar system, reaching the solar system would not be enough. The Sunday may grow brighter. The familiar planets may return to the navigation display. Radio signals from Earth may arrive faster than before. After years of darkness, all of this could feel like arrival. But the solar system is not a harbor. It is a moving structure filled with enormous distances, changing positions and speeds that must still be controlled. A spacecraft crossing its outer edge has not come home. It has only entered the region where home exists. Earth may still be billions of kilometers away. That distance matters, but speed matters more. A returning ship could enter the solar system traveling far too quickly to remain there. The engines that carried it inward may have built a velocity that now threatens the final approach. If the spacecraft cannot reduce that speed, the sun and planets do not become safe destinations. They become objects the ship may pass before continuing outward again. The return can fail, while home is already visible. This is one of the most unsettling possibilities. A crew might spend years trying to reach the sun, survive the loss of fuel, repair failing machinery. It may pull it inward, increasing the very speed that must later be removed. Falling toward the sun does not solve the braking problem. It makes the ship faster. This is why returning from deep space cannot end with a straight inward flight. The spacecraft needs a plan for what happens after it arrives. It may use its engines, the gravity of planets, or a carefully shaped path around the sun. But every option requires the correct geometry, precise timing, and machinery that still works. A weakened ship may have survived the longest part of the journey, only to reach the point where its most demanding maneuver becomes necessary. The engines must start again. The valves must open. The guidance system must understand the ship's real velocity. The burn must last long enough to change the trajectory without leaving the spacecraft powerless afterward. There may be no reserve for another attempt. If the braking burn is too weak, the ship continues through the system. If it is too strong or badly aimed, the spacecraft may fall into an orbit that never approaches Earth. A small error can decide whether the journey ends near home or continues for years around the sun. The solar system is full of possible paths. Only a few lead to Earth. This becomes clearer when we remember that the planets occupy a thin region compared with the size of the space around them. Most of the solar system is empty. Entering it does not mean passing near any planet. A spacecraft can cross the orbit of Neptune while Neptune is on the opposite side of the Sun. It can pass the orbit of Jupiter without ever seeing Jupiter as more than a distant point. The planetary orbits are not rings made of matter. They are paths through empty space. Earth's orbit is the same. Reaching the distance at which Earth travels does not mean reaching Earth. The planet may be hundreds of millions of kilometers away, along another part of its path. The spacecraft must meet the orbit and the planet at the same time. Otherwise, it has returned to the right distance and the wrong place. A ship with enough fuel might enter a solar orbit and wait. It could circle the sun until its path crosses Earth's orbit at a useful moment. But waiting is not passive. The orbit has to be created deliberately. The spacecraft must have the correct speed and direction to remain in a path that will eventually allow an encounter. And the ship must survive the wait. A return delayed by months may exhaust food, power, or life support systems that barely survive the journey inward. The crew may be close enough to receive frequent messages from Earth and still too far away for rescue. They may watch the planet move through the sky while their own orbit carries them elsewhere. The distance can feel smaller. The problem can remain complete. Earth itself is moving at enormous speed around the sun. To meet it safely, the spacecraft must not only arrive at the same location, it must arrive with a motion that can be matched. A ship crossing Earth's orbit in the opposite direction or at much greater speed may have only a brief encounter. The planet could pass close enough to fill the windows, then disappear behind them. A near pass may sound like success after years in deep space, but without the ability to slow or enter orbit, the crew cannot remain near Earth. The spacecraft may be pulled by the planet's gravity, yet still leave on a new path. Gravity can bend the trajectory without capturing the ship. The crew could reach home for a few hours, then lose it again. This reveals a deeper truth about arrival. Distance is not the final measure. Relative velocity is. Two objects can be close while moving apart too quickly for the closeness to matter. A ship can pass within a few thousand kilometers of Earth and still be less capable of landing than a spacecraft much farther away on a controlled approach. The final journey is not about touching the right region of space. It is about joining the motion of Earth. That means slowing until the ship can enter orbit, dock with another vehicle, or approach the atmosphere safely. Every one of these options requires control. The spacecraft cannot simply stop beside the planet. It must fall around Earth in a stable path, or descend through the atmosphere within a narrow corridor. The word return hides this complexity. Home is not a point that can be reached and held. It is a motion that must be matched. A spacecraft approaching Earth too quickly may try to use the atmosphere as a brake. This can save fuel, but it replaces the propulsion problem with a thermal and structural one. The vehicle enters the air at extreme speed, compressing the atmosphere ahead of it and creating intense heat. The atmosphere that makes Earth habitable becomes dangerous during arrival. Too shallow an approach, and the spacecraft may skip back into space. Too steep, and the heating and deceleration may exceed what the vehicle or crew can survive. A damaged heat shield, weakened structure, or inaccurate guidance system can turn the final minutes into the most dangerous part of the entire journey. A ship that survived years in vacuum may fail in the first moments of air. This is especially severe if the return velocity is higher than the spacecraft was designed to handle. Heat shields are built around expected speeds and angles. A vessel coming back from an unplanned deep space trajectory may arrive outside those limits. The crew may be close enough to see oceans and clouds, while knowing the ship cannot safely enter. Earth is there. The route to the surface may not be. This is one of the great reversals of space travel. Far from Earth, a large error may take months to become dangerous. Near Earth, a tiny error can become dangerous in minutes. The closer the ship comes, the less time remains for correction. The long journey was slow. The ending is fast. Mission Control may finally be able to communicate with little delay, but faster communication does not restore lost fuel, repair a failed engine, or strengthen a damaged heat shield. Earth can see the problem almost in real time and still be unable to change the physical limits on board. The return may become most visible at the moment it becomes least flexible. Everyone can watch. No one can create a new trajectory from nothing. This can produce a strange kind of closeness. The crew hears voices from Earth with only a short delay. They see the planet clearly. They may recognize continents, weather systems, and the blue curve of the atmosphere. Home is no longer a faint idea hidden behind the stars. It is directly ahead. But seeing home does not mean the spacecraft can enter it. The ship still carries all the consequences of the journey. The missing fuel, the worn engines, the damaged systems, the exhausted crew, the uncertain trajectory. None of these vanish because Earth is close. The final approach concentrates them. Every earlier problem arrives at the same time. The fuel shortage decides whether the ship can slow. The navigation errors decide whether it meets Earth. The communication delay may have shaped the wrong correction earlier. The aging systems decide whether the last maneuver succeeds. The return becomes the total result of the entire journey. There is no longer room to separate the problems. This is why entering the solar system is only a change of scale. The darkness may feel less empty because familiar objects appear again, but the laws of motion remain the same. The spacecraft still needs energy to change velocity. Earth still moves. Time still passes. Machinery still ages. Home does not become easier simply because it becomes visible. The crew may begin to understand that the final obstacle was never the darkness alone. The darkness only hid the deeper problem. Space has no natural way to bring a traveler back to where they began. There is no restoring force toward Earth, no current flowing home, no road that remembers departure. The ship returns only if every part of its motion is deliberately rebuilt. Even the sun does not guide the spacecraft toward Earth. Its gravity pulls the ship according to mass and distance, not memory. It may curve the path, increase speed, or trap the spacecraft in an orbit that never crosses the planet. The laws are predictable, but they are indifferent to destination. Earth is special to the crew. It is not special to the trajectory. That difference is easy to forget while living on the planet. Gravity holds us to the ground. Roads lead back to cities. Maps remain useful. Home feels like the center of movement, because every ordinary journey begins and ends within the same shared environment. Deep space removes that environment. Returning becomes an act of precise interception, rather than a natural reversal. The crew has to recreate the conditions of arrival, one calculation at a time. If they succeed, the result may look simple from the ground. A light crosses the sky. A capsule enters the atmosphere. Parachutes open. The vehicle touches down. The journey appears to end in a few visible minutes. But those minutes would rest on years of survival and a chain of conditions that could have failed anywhere along the way. The correct solar approach, the correct Earth encounter, the correct arrival speed, the correct entry angle, the correct operation of systems already near the end of their lives. A successful landing would not mean the return was easy. It would mean every remaining possibility happened to align. And if one does not align, the spacecraft may pass home forever. That possibility gives the final approach its quiet fear. A crew can travel farther than anyone before them, turn the ship around, cross the darkness, find the sun again, and enter the solar system, only to discover that none of those achievements guarantee the final meeting. The path may still miss, the engine may still fail, the ship may still arrive too fast. Earth may still be on the wrong side of its orbit. The atmosphere may still be unreachable. The return is not complete until the motion of the spacecraft and the motion of home become one shared path again. Only then can the journey truly end. Until that moment, the ship remains a traveler, even above the clouds, even inside Earth's orbit, even while the planet fills the windows. This is why the phrase "almost home" becomes dangerous in space. Almost can mean a few million kilometers, a few minutes of timing, or a small difference in velocity. Human language makes the distance sound gentle. Physics does not. Almost home may still mean never home. And after following the spacecraft through every layer of this return, the deepest problem becomes clear. Home was never waiting in one place behind the ship. It had been moving through space and time from the moment the journey began. That is why the idea of going back becomes so misleading. On Earth, home feels fixed because everything nearby shares the same motion. The ground, the atmosphere, the oceans, the cities and the people all travel together. We do not feel the planet turning beneath us or racing around the sun. We live inside the movement, so home appears still. Deep space removes that illusion. From far away, Earth becomes one moving world among many. It circles the sun. The moon circles Earth. The entire solar system moves through the galaxy. Nothing remains in the exact place where it once was, and no path is preserved simply because a traveler used it before. The route behind the spacecraft does not remain open. It disappears into changing geometry. This is the final difference between ordinary travel and deep space travel. On Earth, returning often means reversing the direction of a journey. A road can be followed backward. A coastline can be approached again. A familiar landmark can guide the traveler toward a place that has waited. In space, the destination has continued its own journey. The traveler must do more than turn around. The traveler must rejoin a moving system. That means returning to the correct place, at the correct time, with the correct speed, while still carrying enough fuel, functioning machinery, accurate navigation, and human strength to complete the encounter. Every part of the journey has to remain connected to every other part. A failure far from Earth may not become visible until the final approach. A small error can grow. A delayed instruction can miss its moment. A weak engine can create the wrong arrival speed. A damaged life support system can run out of time while the planet is already near. The return is not one problem. It is every problem arriving together. That is what makes the title true. Returning home from deep space is not impossible, because Earth vanishes can remain visible while the route to it disappears. This is a more unsettling idea than simple darkness. Darkness can be crossed. Distance can be measured. A direction can be calculated. But a return requires capability, and capability can be lost gradually, without changing the appearance of the universe outside. The stars remain calm. The sun remains ahead. Earth continues moving. Only the spacecraft's options become smaller. At some point, the ship may carry perfect knowledge and no practical freedom. The crew can calculate the necessary burn, predict Earth's position, and understand the exact sequence that would bring them home. The equations can be correct. The vehicle may still be unable to perform them. Physics does not reward understanding by itself. Knowing the route is not the same as having the energy to follow it. This is why deep space can make home feel both close and unreachable. A radio signal may still connect the ship to Earth. The crew may hear voices, receive images, and know that people are waiting. The planet may occupy a known point on the navigation display. Yet every message reveals another kind of distance. A voice from Earth is already old when it arrives. A reply from the spacecraft will become old before anyone hears it. The connection is real, but the present is never shared. The crew and Earth remain part of one story, while living in different moments. From the spacecraft, Earth may eventually become visible again, as a pale point. At first, it is difficult to separate from the surrounding stars. Then, it grows brighter. Later, the moon can be identified. The two worlds move together against the dark. For the crew, that sight could carry years of memory. For the navigation system, it is still a target. The contrast is severe. Human meaning gathers around the image, while the spacecraft continues treating it as position, velocity, angle, and time. The planet may be the center of every emotion on board, but the engines respond only to physical requirements. Earth cannot pull the ship home because it is loved. The trajectory must still be correct. This is the quiet indifference of space. The laws that allow travel also refuse to care about its purpose. Gravity bends the path. Momentum preserves motion. Light carries messages. Radiation passes through the hull. None of these forces recognizes home. Home exists in the minds of the travelers. The universe provides only coordinates. And yet, the existence of those coordinates matters. The spacecraft is not searching for an imaginary place. Earth is real. It continues beneath clouds and sunlight. Oceans move. Weather crosses continents. People sleep, wake, and look toward the sky. The planet is not gone. It is simply difficult to rejoin. That distinction preserves hope without making the journey easy. A ship with enough fuel, a healthy crew, functioning systems, and a precise trajectory could return. Deep space does not forbid every return. It makes return conditional. The conditions become harsher with distance. Farther travel means more velocity to change, more time for systems to age, more delay in communication, more uncertainty in navigation, and more opportunity for small failures to grow. Eventually, the collection of conditions may exceed what one spacecraft can carry. The impossibility is not always absolute. It is practical. A route may exist in theory, while no real vehicle can survive or afford it. This is often how the universe limits us, not by breaking the laws of physics, but by making the cost larger than the resources available. A human can understand the path to another star. Engineers can describe the speed, shielding, energy, and time required. But description does not reduce the scale. The same is true for coming back. The return may be allowed by physics and still be impossible for the ship that needs it. That is why the decision to travel far from Earth would have to be made with unusual honesty. A mission cannot assume that home remains an easy option simply because the planet still exists. The ability to return has to be designed, carried, protected, and constantly recalculated. It is not a promise built into distance. It is a fragile capability. This is why deep space exploration may eventually force humanity to think beyond the idea of return. Some missions may be designed as journeys outward, with no realistic way back. The destination may become the new home, or the spacecraft itself may have to serve as one. That possibility changes the meaning of departure. Leaving Earth would no longer be a temporary absence. It would be separation. A crew traveling to another star may know from the beginning that Earth will never fill their windows again. They may receive messages for a time, watch the sun slowly fade, and carry recordings of a world they cannot revisit. For them, home would survive as memory, culture, and data, not as a destination. This is where the story of returning home becomes the story of what home actually is. Is it the planet itself? The people living there? A familiar sky? Gravity beneath the body? The sound of weather? The knowledge that every breath is supported by a world rather than a machine. Deep space takes these ordinary things and reveals how much they depend on being near Earth. Inside a spacecraft, air must be manufactured, water must be recycled, temperature must be controlled, waste must be processed, light must be produced. The environment does not support the crew naturally. The crew survives because the ship imitates a few functions of home. But imitation is not the same as a planet. A machine can provide oxygen without providing an atmosphere. It can provide light without a sky. It can provide food without soil and shelter without a landscape. It can keep the body alive while leaving almost everything associated with ordinary life behind. This may be enough for a mission. It may not be enough forever. That is why Earth becomes more meaningful with distance. From the surface, the planet can feel like a background that has always existed. From deep space, it becomes a complete life support system on a scale no spacecraft can reproduce. Earth carries its own air, water, weather, gravity, chemistry, and living cycles. It repairs, changes, and continues without a crew operating every pump. A spacecraft can imitate part of this for a while. It cannot easily become another Earth. The farther the traveler goes, the clearer this becomes. Home is not only the point from which the journey began. It is the environment that made the traveler possible. The body was built for Earth. The senses were shaped by Earth. The idea of normal was learned here. Even the desire to explore space began beneath this atmosphere. A returning crew is therefore not simply trying to reach a location. They are trying to re-enter the only environment their bodies and memories fully recognize. That is why the final approach would carry such power. The blue of the oceans, the white of clouds, and the thin line of atmosphere would not look like ordinary features. They would look like systems that no machine on board can replace indefinitely. The planet would appear fragile. It would also appear complete. The spacecraft approaching it would be small, damaged, and dependent. Earth would continue turning, vast enough to hold weather, forests, cities, and billions of lives. The difference in scale would make the return feel almost impossible, even in the final hours. A machine is trying to meet a world, and the world does not stop moving. If the meeting succeeds, the crew becomes part of Earth's motion again. The spacecraft enters orbit, descends, or docks with a vehicle capable of reaching the surface. Velocity is removed. The long separation becomes smaller until the travelers are once again held by the same gravity, atmosphere, and daily movement as everyone below. Only then does home stop being a target. It becomes an environment again. The instruments no longer need to predict where Earth will be because the crew is moving with it. The planet feels still once more. The enormous motion through the solar system disappears from ordinary awareness. Home returns to being simple. But the simplicity is an illusion earned by arrival. The crew now understands what it means to share the planet's motion. They have seen what happens when that shared movement is broken. They know that returning was never about following a line backward. It was about rebuilding a connection to a moving world. And if the meeting fails, Earth continues without them. The planet completes another orbit. The sun moves farther through the galaxy. The spacecraft follows a new path. The distance may begin growing again, slowly at first, then beyond any remaining possibility of correction. Home remains real. It simply becomes unreachable. That may be the final fear hidden inside deep space. Not that Earth disappears, but that it can remain visible, known, and loved while becoming physically impossible to reach. The crew does not lose the concept of home. They lose access to it. And in the end, that is why returning home from deep space is impossible in a way ordinary language cannot fully express. The problem is not one wall, one failure, or one wrong turn. It is the need to bring motion, time, energy, machinery, navigation, and human survival back into alignment around a planet that never stopped moving. The ship has to find Earth. It has to reach Earth. It has to match Earth. It has to survive Earth. And it has to do all of this before its remaining options disappear. Deep space offers no road home, only a brief possibility of meeting it again. Thank you for watching this calm journey into the hidden difficulty of returning to Earth from deep space. If you enjoyed this documentary, subscribe for more quiet space stories like this. Leave a like if you want more deep journeys into the mysteries of the universe. And write in the comments whether you would accept a one-way journey into deep space if it meant becoming the first human to reach another star. Tonight, you were watching the Just About Space channel, talking about why returning home from deep space is impossible. Sleep well and keep looking up. Good night.